1, 1. So we have this triangle, and that triangle is being rotated about the horizontal axis. That's problem number 3, review Calc 2. You guys also Calc 2? Excellent. Horizontal axis. So if this thing rotates like that, right? That point stays put. This one goes around and it will form like a big circle. And this one goes around and forms like a smaller circle. So more or less, what we have is something like this. Let's look at the formulas in the lesson, and remember that you can have a sheet of notes of any kind, double-sided, but you have to be able to see it from far away. It means we don't want you to put too much because it's just stressful. And yes?
Wait, so if you're doing the prompt, you're also going to have a
Yes,
sheet?
the conditions are identical.
Okay.
They know that you're allowed to have a sheet, but you have to show it to them. And it has to be handwritten. So let's see, let's look at the lessons. So would that be volume by cross sections or volume by cylindrical shells? What do you think?
Cross section.
Cross section? Okay. What is the difficulty in the problem? Why did you ask me to do that?
I don't know, I didn't get it.
You didn't get it.
Yeah.
Where were you stuck? What? Setting up the formulas or
Yeah, setting up the integral.
the integral, right? The general formula in the lesson basically is set up by looking at, let's see, looking at the little, what do they call it? Like a little cylinder, and then integrating as you cut the solid from the first moment that you hit the solid until the last one. So there are 3 things you need to determine here. Where to start integrating, where to put that knife from the beginning, where to finish the knife, so these are the limits of integration. And then the 2 functions that determine the solid. And the formula that you see is this one. The formula for the volume of the solid of revolution is from A to B, F of x squared minus g squared of x dx. But that, you have to make sure that you're rotating this around the correct axis. So that don't have a look at that. That formula is when you rotate about the horizontal axis, x-axis, and that's what the problem says. So that's okay. So we need to determine A, B, F, and G. Yes?
If you were to use the other formula, would you just be solving for the y variable, and solve for the x variable instead of the y?
I think so. Yeah.
Okay, so theoretically you could use the other formula, you just need to
Yes.
substitute.
Yes. In most cases, actually, in all cases, you could use both formulas, but sometimes it's much easier to use one formula than the other, depending how the problem is set up. In this case, I think it's more straightforward to just determine F and G and A and B, right? So for A and B, for the left limit of integration, that's clear that if you cut it, if you have a knife slicing it here, you're not going to hit anything, right? So we might as well start at the first moment, which is at 1, and you finish at this point, and that point was 2, 0. So that 2. So our integration will be then from, remember this was 1, 1. So from 1 to 2, and now we need to determine F and G. So this will be our F, and that segment would be G. both are linear functions.
Yeah.
Right? These are segments. So now we go back to high school, and then we have to ask ourselves, how do we determine an equation of a line that passes through 2 points? And that would be F, and that would be G. That one is so easy to guess because you basically move 1 unit to the right and 1 unit down. So I can guess that the slope will be -1, so it'd be negative x plus something. And then that plus something will determine if you extend that line, it probably will hit the horizontal vertical axis here. So negative x plus 2. I am not spending more time on it, how to determine the equation of a line passing through 2 points, because that's really not even calculus. That students should review this from, what, algebra, pre-calculus? But the key word is 2 points, determine the line. So G will be negative x plus 2, and then this one, I think it has slope. What was that point? Do you remember the coordinates?
2, 4.
2, 4, right? So if this was 2, 4, this was 1, 1. So F would have, the slope is 3 divided by 1. And this, where would that hit the horizontal axis? Can you tell me? The picture is not very clear, but I can also determine that number easily. If I just plug in 1 for x, so I get 3 times 1, that's 3. And the y coordinate of that point is 1. So how do I make 1? If I already have 3, I have to subtract 2. Sort of my way of getting an equation, but you all are used to getting equations your own way. So, assuming that I didn't make a mistake, which I'm about 90% correct, the formula then is 3x minus 2 squared, that's f, minus g of x, negative x, plus 2 squared dx. To solve that integral, you would use quadratic formulas here, and eventually you would get a quadratic equation, polynomial, second degree. So the integral would be an antiderivative. You would use these formulas, so it would be some kind of a cubic polynomial. And then you evaluate that polynomial at 2 minus that polynomial at 1. I'm pretty sure, but I will leave it to my colleague, Professor Shimoni, whether she would want you to really get the number. Chances are that we just care about solving the integral up to, you just plug in the number without evaluation. Yeah.
Would you be able to do U substitution instead of doing a quadratic for each of these?
What would be the U substitution here?
3x minus 2 equals u squared, and then you can separate the integrals with one integral.
That is correct. Let me say that comment again. Your suggestion, which is correct, is you could split that integral into 2 integrals and work out each integral separately. Maybe that's even faster. If you split that integral into 2 integrals, you would get then the integral of 3x minus 2 squared dx, that's the first one, minus the integral of negative x plus 2 squared dx. And for this one, you could use the U substitution. It would be faster and easier. That's correct. But then you still have that one to work out. So at the end, I'm not sure if you're saving that much time. But I'm sure you exercise that at home, and you probably have more experience than I do. So the key, to summarize, is use the correct formula, get much better picture than mine. My picture was not really good, and that's why I said I'm only 90% sure that I got the functions correctly. Spend more time, use the grid if you have it on your paper. If not, make a grid to make sure that you don't make that mistake with the slopes. But otherwise, that's what we look for, to the correct application of the formula, and knowing that you know what's going on with the integral, that you just don't apply formulas without thinking. Because that's the greatest danger in the future, that you will be engineers, you will be scientists, and somebody else will give you a complicated formula, and you say, I know how to do it, you just put the numbers, and you get, well, you get something wrong, because not realizing what's going on behind it. So picture is very important. Okay, next question, please.
So the fourth one?
4.
Yeah.
So I'll just comment on the 4.
Yeah, you can.
So if we are looking at problem number 4 from the review, problem number 4 is somewhat similar. It's actually has the same triangle, but now we're rotating about the vertical axis. Okay. So why is it a tricky question, or is it any different than the previous one?
No. It's kind of similar, I guess.
Yes, but you have to look at it differently. That's the thing, is you have to twist your head and make sure that you don't confuse the horizontal with vertical axis. So you have to make the vertical axis horizontal if you want to apply the same formula. So I would even switch the picture and replace the role of x and y. But it's still the same, there's nothing new in it. Yes.
If you were to use the other formula, you don't have to adjust.
Correct. And maybe this is why actually using the other formula that you're referring to a different lesson, right? How do we call the other formula?
Cylindrical shells.
Cylindrical shells, yes. Because that formula is already given as a function, as an integral, where you rotate things about the vertical axis, right? So I'll just remind those of us that don't remember the other formula. You can have that formula on your sheet. So that's the integral of 2 pi x, and the difference is f of x minus g of x dx.
Eric?
Yeah.
I'll meet you at room 2.
Okay. Yeah. It may be that it might be a little bit faster. If somebody is less comfortable with flipping the, your exam, and I would probably use this one.
I guess I have a question about the exam,
Yeah.
or a couple actually. First of all, how long is it going to be? Is it going to be roughly the same length as these review problems, or is it going to be shorter?
So I haven't. I let my colleague write the exam for tomorrow. I think the best hint that everybody got was the list of topics that is on Piazza.
Oh, okay.
There are 7 problems, I think, 6 to choose from, and I think they will be slightly shorter, but the ones like 3 and 4 are perfect examples of problems that we could put in, because they are short and they tell us whether you understand the main idea. We are looking not for difficult problems on the exam. We want to test whether you remember and you know how to apply the main idea from each lesson. And my notes, basically, if you look at the first, second, or third section, usually there's just one main formula. So that's what we'd be looking
Oh,
for.
where can I find the list of topics in the Piazza? What's the post called?
It's called
It's
Math 2.
Okay, you had another question?
Yeah, let's say they're rotating about a different axis, like a
Diagonal axis? Or a different meaning?
different meaning, if you were rotating about like x equals 2, x equals 3,
Okay.
are you doing the difference of x from whatever you're using? So if we're using the horizontal one,
It's a good question. So if the axis is still horizontal vertical, but it's not one of the coordinate axes, right? Does anybody have a suggestion what you would do in that case? Yeah.
could you use
I
the
would shift
difference between the two?
Yeah, of course. But if you can use the difference, but then the center of rotation will be different. So what I would do is I would take your paper and shift it so that the axis becomes one of the coordinate axes. In other words, once you determine f and g from the problem, these wouldn't be f and g to put into the formula. You have to modify them by that shift. So for example, if the original f is, let's say, x squared, and they tell you rotate but not about the horizontal axis but about x y equals -1, then that parabola is actually, you have to shift it 1 unit up, right? So it'd be x squared plus 1 in that formula. So to summarize, I would reframe the problem so that you could use the wording rotating about the horizontal or vertical coordinate axis. So I would adjust f and g that way.
Would you be able to, so it's f of x, would you be able to do x like plus or minus? Is that what we're talking about, or do you
Yes.
mean? Okay.
Yes, yes. So,
To my understanding by what you're saying, I would think that you're doing x plus 1 squared rather than x squared. plus
correct, correct, yeah. Well, you have to be careful about which axes you are rotating, but the basic idea is, if let's say one of the functions is this, and now let's say that you want to rotate this, but not about the horizontal axis, but about this line, y is equal to -1, then I could it's equivalent if I look at this problem as this. I'm going to rotate about the horizontal axis, but my region now is this. So here the function was just x, well, it was some parabola. But now whatever the function was here, you have to add to that 1, because now it's one higher. And if the g function for this problem was actually 0, so the bottom function here is 1. So you add 1 to f and g.
I'm asking, I'm a little confused upon
Yes.
if you are adding to, if the, like let's say f of x equals x squared, are you adding to within the parentheses or outside? Is anything on the outside
You're right. That depends on whether you're going to rotate about a horizontal axis or vertical axis, and that depends on which formula to use. That's why I didn't answer
Right.
that. There are 4 combinations. The main thing, if we have a problem like that, we would be looking at your reasoning, how you convert that to one of the 2 formulas. The best thing is to ask yourself, well, how do I make that axis, how do I make the axis of rotation one of the coordinate axes? You know, how you have to shift it so that you can apply the formula.
Thank you.
Sure. Other questions from different topics? Yes.
Oh, I guess this is the same topic.
Okay, because we have about 40 minutes, but I can address your question.
Okay,
quickly.
really quick. So, in your lessons, you have one formula for rotating about the y-axis and one for rotating
Yes.
about the x-axis, but they're both functions of x. So, if you had a function of x and you wanted to rotate it about the y-axis, could you just find the inverse of that, or
That is correct.
and
And
use the
yes,
formula?
yes, it's an excellent idea. It's a correct idea. Yeah. Sometimes, if the problem doesn't have all things ready for your formula, you may have to solve for the other variable before you plug it in. The best way to check if you're setting things correctly, look at that letter here. If that's dx, that means you're rotating about the in this formula about the horizontal axis. Make sure that these, whatever you put in here, that these are functions of x. And if they give you as functions of y, you have to solve it. You have to get the inverse functions. That's an additional difficulty, and I think we had that in homework problems. I'm curious whether my colleague decides to put it on the exam. I'll leave it at that. Other topics, please?
So if you have to rotate the same triangle about the I mean about the y-axis, should you take the inverse of those functions?
Yes.
Okay. And put that in that equation?
It depends which formula you want to use. If you want to use this, yes.
Yeah. Okay.
Yeah.
Series versus sequence. How to distinguish between the two?
Sure. The difference between series and sequences. So, every series is a sequence, and you can also make every sequence a series. So I'm definitely not helping you with that. But now, in practical terms, a sequence is a list of numbers separated by comma or by your favorite character. Now, to make out of this a series, I will make a new sequence out of a given sequence. If you start with, let's say, sequence A0, A1, A2, etc., I can make a new sequence called B0, B1, B2. I'm just adding numbers, and these are called partial sums. So if, in particular, if I start with the harmonic sequence, 1/2, 1/3, 1/4, 1/5, and so forth, then the corresponding series would be this sequence. But to save time and space, we just write this as summation from I equals 1 to infinity of 1 over I. So that actually represents either this sequence of partial sums or just its summation if it has a limit. So that's the abbreviation, sigma from I equals 1 to infinity. I'm sure if you took Introduction to Computer Science, they have all kinds of commands for summation, sum, and so Mathematica has the command sum, S-U-M, and so forth. The main questions in these topics are whether a series, if you add these numbers, whether they keep on adding to infinity, whether they keep on adding and there's no bound for it, or if there is a bound. The two words for these topics are convergent and divergent. Pictorially, if you're going to be adding these steps, so let's say this step is A0, then A1 is a smaller step here, A2 is even a smaller step, right? A1 is 1/2, 1/3. So imagine an animation that just lists all these steps. The consecutive one is smaller and smaller. And the question is, if somebody gives you some number, n, some point, if you have as much time as you want, if you wait long enough, if you eventually pass that number or not. If you can have that game over and over again, you ask somebody, give me a number. Okay, somebody gives you a number. And you have infinite amount of time. You wait, and always that sequence, that stepping animation goes beyond that number. That means that the series diverges. It goes to infinity. If, on the other hand, I can give you a number, and you can wait up to infinity, up to the universe collapses, and these, you still be adding stuff, but small enough that you will never pass that number, then the series will converge. So the last 3 weeks were basically devoted to technologies, how to determine if something converges or diverges. So if the limit exists of a series, it doesn't. Yeah.
Would we, for the exam, we're basically just going to be trying to apply the tests that
Yes.
is in the book?
Yes. I think the problems will be, which I don't personally like that much, they're more mechanical. What I just mentioned here is much deeper understanding of what's really going on. A series is just another sequence, but the way you form a sequence is you have these building blocks. You just add.
Can you look at the problem 40 from the
Sure.
48?
we look at the review,
Yeah, review 40 A and D.
and we look at problem number 40,
Yeah.
A and D. Actually, unlike most students, well, perhaps you're an exception, but I actually like the topics on series and sequences. Many students don't like. It's at least easy to prepare these because my vocabulary is the two words: convergence, divergence, convergence, divergence. I can even deliver these lectures in any language you want. But let's look at problem 40A. We need to determine whether the series 2 to the k diverges or converges, and if it actually converges, probably, if I were to put that problem on the exam, I would probably ask you to even tell me what the limit is. 1 over 2 to the k, so the first element is 1/2, the next one is what? 1 over 4, right? 2 to the second power. The next one is 1 over 8, 1 over 16. That's actually one of the most basic series that computer scientists know. Right? Each next step is half of the previous step. So that's related to this paradox of an arrow, whether it passes some number or at some point or not. This is a geometric series, right? Because then the subsequent term is twice as small as the previous one. So if it's a geometric series, then you even have a formula for it, and you can evaluate. But they just ask you to say that whether it's convergent or divergent. So this series converges because it's a geometric series with let's say G being 1/2. In general, a geometric series is of the form, I think, A G to the power K.
K minus 1.
Oh, K minus 1, yeah. Sure. To infinity. Right? So that number A here, you could say that's 1, and then G is 1/2. So I think in the notes I gave you the formula for it, but that one I remember by heart, that if you add 1/2 and then 1/4, you're going to get in the limit to 1. Part D, yes?
It might just be because I'm not that, I don't understand the topics that well, but why can't you just take the limit to infinity of almost every function and then go ahead and decide the conversion?
Because if I take this function 1 over 2 to the k, and k goes to infinity, I will get 0. So if I add zeros at the limit, well, one would think, well, it's got to be 0, so it's got to converge. And here is the trap. Look at this function, this series, the harmonic series. The term 1 over I, as I goes to infinity, goes to 0, right? 1 over something that goes to infinity is in the limit is 0. So we would have the summations of things that go to 0. So naively we may think that actually this has got to be divergent because we're getting tiny things. But in the lesson I think we proved that actually that goes to infinity. So you may have things as sequences that say an goes to 0 in the limit as n goes to infinity, but the summation of these an's might still diverge to infinity. The classical example, and perhaps the most important, is this one. This is unlike your intuition. The term goes to 0, but even though we're going to be adding very, very small numbers together, time permitting, they will exceed any barrier. So that's why we cannot just take the limit of that function. But they converge, they diverge very slowly. it takes a lot of time for this series to go beyond 10. I think it was like billions. You would have to go up to maybe I equal, I don't know, 10 billion or even more to reach number 10.
But there's like a formula that you can find out where you can say how long it takes
Yes.
to get to a billion and it'll spit out a number.
Yes, there is a formula that's not an exact formula, but that's what mathematicians in analysis do. They estimate how long it would take. Yeah. They, more or less, this goes as fast as logarithm, natural logarithm. So remember the graph of a natural logarithm? It's pretty flat eventually. Like logarithm of a million is probably, natural logarithm of a million is probably, I don't know, maybe like 20 or something. They're very small number. That's a very good question though. So you do have some intuition that for a series, it's not enough to just look at the term itself if it goes to 0. If it doesn't go to 0, then you have a guarantee, yes, that series cannot converge. For example, if the term itself eventually will be very close to 1/2. So every time we add a new term, we move the sum by 1/2. So that means that eventually we're going to go to infinity because we are always moving by something that's bigger than 0. So we're progressing. But the other way, it's not necessarily the case. If a term goes to 0, this is precisely where we have so many theorems. We don't know. We have to use some other test. Yeah.
So if that question appears in the test, how do we prove it?
You don't have to prove. You just say it's a harmonic series, so it diverges. You remember it from the theory from the lecture, or you can say it is a p series. Remember, we studied p series. I think I wrote them as I to the p, or what letter did I use? N or I in the
P.
lectures?
Then
I forgot. N
Mhm.
probably. N starts from, let's say, 1 to infinity. And this series, there's a theorem in the course that if p is greater than 1, that implies that the series diverges. But if p is 1 or less, then the series if p
It's
is
the opposite.
the opposite. If p is bigger than 1, then the series converges because that gets smaller faster. If p is 1 or less, then the series diverges. P being equal 1 is this. That's the first example. So just to sum up, if something like that is on the exam, you say it's a p series with p equal 1, so diverges. So the series diverges. Okay, we have time for, let's say, 5 more minutes. Yeah.
Right here, so the geometric series definition, I don't know if this is a mistake. So
Mhm.
it's AR to the n minus 1 is equal to A over 1 minus
Yes.
R. That's the ratio.
Yes.
But it says if the absolute value of R is greater than 1, shouldn't it be greater than or equal to 1? Because if it's 1 minus 1, A over 1 minus 1, that would just be...
Right, so let's figure out. Maybe there is a mistake, maybe not. We are talking about the geometric series. Can you read off exactly how I presented it?
Okay, let AR be numbers and let A n equal to 0. Then the summation from n equals 1 to infinity of AR to the n minus 1 is called a geometric series.
That is a geometric series. Okay.
Yeah, and so it says, in the case that the absolute value of R is less than 1, the series converges.
So if the absolute value of R is less than 1, then this summation converges.
Yeah, and then it says, and then it has like the ratio definition, A over 1 minus R. And then it says, in the case that the absolute value of R is greater than 1, the series diverges. What if it is 1?
So I missed one case, right? I tell you what happens if R is it has a modulus less than 1 or bigger than 1, but I'm not telling you when it is 1. Well, what do you think? Let's say a is equal to 0, then it's an easy case. It's just summations of zeros. So
well,
it's
it's just 1 plus 1 plus 1 plus 1 plus 1.
right. If a is not 0, then you will have whatever that number a is. Let's say it's 1, right? So it'd be 1 plus 1 plus 1 plus 1 plus 1 plus 1. So is it divergent or convergent? It divergent.
Okay, I was just confused because it didn't include the case of 1.
It's a very good observation. So we both are correct in some sense. This is not a mistake, but it's an omission. Why did I omit that? Because in this case, there are two cases actually. If a is 0, it's a boring case. It's just zeros, right? But in other cases, it's just sum of constants. So I could have added that if r is equal to 1, or then you have divergence. But here is now I remember why I missed that. What about if r is equal to negative 1? Then you would have 1 minus 1 plus 1 minus 1 plus 1. What is that series? Is that a convergent series? Or?
Alternating series.
Yes, but alternating to where? To what number?
0.
Well, depends. If you like if you want to stop at odd numbers, it will be 0. If you stop at even numbers, it would be 1. But you're not supposed to stop.
Couldn't you also say it?
So it's divergent, by the way. It's divergent.
So they're both diverging.
Yeah, but,
Both cases, right?
yes, but one diverges going to infinity.
And one diverges.
That just
not
alternating, not having a limit. Like it oscillates between say 0 and 1, 0 and 1, 0 and 1, 0 and 1. Yeah. So I could have added that. Yeah.
Drawing a parametric curve.
Parametric curves. Okay. So that's a recent topic, right? I think it was 26, and it would be probably the last topic we'll cover, and it's the last topic in the course, I think, or one of the last ones. Parametric curves
Do we
are.
have slope fields on the exam?
Um,
No.
No.
I don't know. Did she list?
No.
those? Then probably not.
Thank God.
Yeah.
Slope fields could be actually a lot of fun. Depends what the problem is, right? If they want you to just draw, like a parking lot. So I think of slopes as just slope fields as basically like if you're very nearsighted, you drive and you have a parking lot, and all you can see is just one arrow here, and you don't see another one until you pass that one. So you're basically tracking a curve. And these arrows are just little derivatives. They just tell you the direction in which you go. There's a lot of applied mathematics related to slope fields to differential equations. If you are going to be a civil engineer or any type of engineering, then they'll have a lot of them. Do you have a specific question?
Mainly on how to draw them if you were given functions.
Ah, okay. Well, the modern technique is ask Alexa. Alexa won't do it. Alexa is not capable of drawing it for you yet. We'll wait a little bit longer, but if you actually ask Wolfram Alpha, it will do it. That's why you won't be able to use any device tomorrow. I would, let's say that we have a parametric curve. For example, cosine t sine 2t, and I would ask you to draw this curve. I would prepare a table and let t vary. Let's say pick maybe 4 or 5 points for t. So, and I could start with t, then the first coordinate, the second coordinate. For example, if t is 0, then cosine of t is 1, sine of 0 is 0. So then once I already have the first point, I mark it in the Cartesian coordinate system, which will be 1, 0. So 1 for cosine t, 0 for sine t. And then I take another point, of course it'd be easy to just pick pi or 2 pi. Or I'll pick, say, pi over 2, which is more or less 1.7. But it doesn't matter what that is, right? Because I'm looking for the horizontal and vertical coordinates. Cosine of pi divided by 2 is 0. Sine of 2 times pi divided by 2, sine of pi is 0 as well. So the next point would be, say, 0, 0. That's the second point. But that's still very few to make a curve. So it would be interesting to know how would I draw a line from 1, 0 to this one. But I don't know how. So probably you would want to add another point maybe between 0 and pi divided by 2 to have a better idea where you draw. So I put just pi over 4, and then cosine of pi over 4 is root 2 divided by 2, so it's more or less 0, 7. Then sine of that would be sine of pi divided by 2, so it'd be 1. So somewhere here, we would have another point, 7, comma 1, etc. It's good that you ask how to do it manually. In most cases, you would ask a computer to do it. Usually with parametric curves, you get these flowers, things that repeat. If you have trigonometric stuff, you get beautiful stuff that just go like that. Yeah.
I know that it wasn't listed as one of the topics, but
Sure.
I know that Euler's method is also a thing that's pretty closely related. Would we be?
Yeah. So it's what's not related. Probably, I used to put that on the exam. I don't know if my colleague has been doing this. Euler's method is this method where you find an approximate solution to a differential equation by predicting where the next stopping point might be. The differential equation gives you the derivative, so it gives you the direction in which you go. Then the Euler's method has a step. So you go 1 unit to the right along the direction that the derivative tells you. So that gives you like the next point where you should mark your stopping point. And you continue doing this. It's a little bit like those games where you're in the forest and they tell you, okay, you gotta go northeast for let's say 1 minute, and then you will have new piece of information. You just go like that. And the solution becomes more accurate if you can verify, calibrate your direction more often. That's where Euler's method becomes more accurate. When that step, maybe I use the letter H for the step, is getting smaller and smaller. Computers do that too. They have an Euler's method incorporated.
So I have one question.
Yeah.
One last question. The 23rd G.
Pardon me?
23 G.
A review?
23, yeah.
So we go back to the review session and we look at 20D.
No, 23 D.
23D, of course. For which of the following series determine if they're convergent or divergent, illustrate and name the test you are using. You ask for D, right?
Yeah.
Okay, so I'll write it down and that will be our last question. D is summation from n equals 1 to infinity of -1 to the power n cosine 2 divided by n. Well, first of all, I'm looking at it and I see that as n is large, because that's only we care when n is large, the tail means like when n is large, actually determines if things converge or diverge. The first couple terms don't matter. They don't change the behavior of a series. They may change the value, but they don't change the behavior. So if n is very large, what happens to 2 over n? It gets very small. So cosine of a small number close to 0 will be close to 1, right?
Yeah.
Close to cosine of 0. So that will be close to 1. So then we will have something that alternates, depending if n is odd or even. That just tells you the sign, right? So it'd be something close to 1 with a negative sign, plus something close to 1 with a positive sign. So what do you guys think? what would happen with that series?
Converges.
Well, isn't it like minus 1 plus 1, minus
Yeah.
1 plus 1, minus 1 plus 1? So that one is only bounded, but actually does not converge because it will oscillate between two values. But okay, so if you were to write this what I just said, perfect. We would be thinking, oh whoa, didn't even mention the name of the series, so probably understands it but didn't study it. Which would be good. We'd be very happy. We would grant that problem is done for your talent of passing the class without even looking at the test. But most of you will actually name a series here.
So what can you name for that?
Well, it alternates, right? We observe that the term doesn't go to 0. And remember, for a series to converge, what's required, what's necessary?
It's go to 0.
That the term go to 0. The term does not go to 0. So we can say, because each term, the term in the limit is 1, right? Not 0, the series cannot converge. The formal statement, I think, was that if that's called an, right? If the limit of the absolute value is not 0 but something bigger, then that implies that this series must diverge. And that's the case here. If n goes to infinity, this goes to 1, so that just changes the sign, so the absolute value of it goes to 1. So that limit doesn't have, the series doesn't have a limit.
This is the alternating series test.
It is an alternating series, but it's not an alternating series test. The alternating series test, and it's good that you mentioned that, so I'll illustrate this.
So can you say that series is divergent now?
It's divergent. Hopefully, I will be able to shed some light on the confusion. This is an alternating series. There does not exist a limit. There's no limit here. Because every time you calculate so far the value, there'll be either 1 or negative 1, 1 or 0, 1 or 0, 1 or 0. So it never stabilizes. Now, 1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6, etc. This series converges because of the alternating series test. An alternating series test says if, these are the terms, right? an. If an goes to 0, and if a series is alternating, then the series converges. And now, many of you should be confused again, but wait a minute, didn't we have a conversation for 10 minutes that if the term goes to 0, that's not enough? And here I'm saying, well, it is enough. But that's only true if the terms alternate. Because if they alternate, they go like this. To the right a little bit, then to the left, but less. To the right, but less. To the left. So they go like zigzagging, but that zigzagging is smaller and smaller. So they zigzag, squeezing the limit. Now, if you only move in one direction, to the right, even less to the right, it's not clear. So the fact that you have pluses and minuses, then your first comment, which was, isn't it just enough to take the partial term and see if it goes to 0 or not, then you're completely correct. If it's an alternating series, then there's an equivalence between if the term goes to 0, then the series converges. The more difficulty that we face is if we have all the terms that move in one direction. Then that's where the depth is, because we don't know if they will slow down to the point that they will not pass a certain limit, or they will keep on going, and every obstacle that you will give them, they will be able to pass. Appreciate you took the course. Stay in touch. We want more math majors. The best job on the planet is actually a mathematician. You're smiling. They actually make more money now than engineers. They're the ones who innovate. They're the ones who create new products. There are more mathematicians now in Silicon Valley than ever. The job is stable. And seriously, Google how much they make. More than us here in the department. Good luck tomorrow. And really thank you for uploading it. Yeah, so.